And the first speaker of the last session will be Steve Childress, who's going to answer the question, how fast can vorticity stretch itself?
You've got to be kidding. Anybody who can answer the question is well on their way to that $1 million. Mind you, $1 billion is not what it used to be, but still. Another thing is, I think that the question has been poorly posed. It should be for Euler's equation, not Navier-Stokes equation. That's a personal opinion, though. I mean, anyway. I would like to talk about Euler's equations. And the question of how a bundle of vorticity can stretch itself due to the interactions of the lines inside the bundle. And I've put this, the thing crashed, so I can't show it to you now, but you've seen the video of the colliding vortex tubes. And there's a lot of things to think about in this video and to imagine. And in particular, by the way, is this, can you hear me? Yes. One thing is that this is, of course, a viscous calculation, and I would like to imagine what would happen if that experiment was done. First, let's have a little knob where we can, each time we run it, we lower the viscosity some more, and we see what happens. Now, a lot of us might, I think, would conjecture that we'll see something similar. The thing is going to explode at a certain point, irrespective of what that viscosity is, but there's going to be finer and finer scales, and perhaps even at about the same time. I mean, I don't want to take that leap, but anyway, something is going to happen that's sort of similar. That's because of a lot of instabilities, and this thing is leaving whatever axial symmetry it possessed at the beginning. But let's imagine also we have another knob that will turn off everything except axial symmetry and get rid of all possible instabilities. Now, I would assume that the initial value problem for that axisymmetric problem has a solution of some sort. Something's going to happen. I would imagine it might just keep expanding. And then the question is how fast, if it does keep on growing. By the way, it's not, I don't say if that's always going to grow. I don't know, it could do something strange. But if it is always growing, and we know in the axisymmetric case, there can't be a finite time singularity, so it's going to be doing something. But let's suppose the vorticity keeps growing, then what is the rate of that vorticity as t goes to infinity? I mean, this is a mathematical question that one could ask. And it has nothing to do with local instabilities, which are exponential, anything of that sort. What really happens? This is a hard question. And of course, it is the question that leads to the problem of finite singularities, yes or no. So what I'd like to consider, of course, a line cannot stretch itself. When you talk about stretching, you have to talk about an open set of vorticity. But if we consider a line, and we look at the equation of motion of that line due to some velocity field with components u, v, and w in the local Frenet system, and we differentiate this with respect to S0 is a Lagrangian coordinate along the line, and we get the Jacobian by taking the tangential component of this. You end up with two terms, one of which is here, the normal velocity curvature in the Jacobian, and here the rate of change of the tangential velocity along the line times the Jacobian. And this is kind of the stretching term of really pulling out as points separate along the line. That's easier to understand. This is the kind of expansion stretching, if you like, as a line with curvature moves normal to itself and has to get longer as the ring expands. And of course, you can, by having anti-parallel vortices, these can cause each other to do this, and so it's a way of getting vortices to stretch. And the other term here, well, you can imagine pulling on a tube, and somehow another way is to think is compressing a tube, squeezing it down, because as you squeeze it, you shoot out fluid, and that stretches the particles at the axis. So another way is to squeeze. That's hard to do, though. Anyway. This sort of thing, this tube can sort of stretch this one, but they also deform. One can imagine even, I was discussing this with Keith, having a knot then something similar is going to happen, but I don't know exactly what that would be. It would be nice to have, now that we have knotted vortices in the laboratory, I understand, to have one like that we could see what it would do. Could it shrink? Whatever. I don't know. Anyway, these are the available mechanisms for working on the line, and they've been exploited many times by many people to investigate how fast vorticity can grow in Euler flow. Well, we know the equations, and I'll think for the most part in infinite space, not completely. For the most part, a compact initial set of vorticity with finite energy and so on. What can happen? Well, we can get the finite time singularity. The Beal-Kato-Maida condition, of course, tells us what must happen if the singularity develops. It's an excellent test. It's widely used. We may have global regularity in time, with the vorticity actually going to infinity. Some people say it's exponential, some super exponential, whatever. The maximum W might be bounded. Well, it certainly is if the condition that you start with happens to be a steady flow. It could be for other flows. I just don't know. But in particular, something I just think anything that we're talking about here that's really getting high vorticity, it's bound to be so unstable that that the closer we get, the more unstable it's going to be. And so I sort of have this picture in my mind that we're dealing with a very unstable object. But you can, of course, approximate it. And this is a sort of pessimistic thing, but I just don't know. It's certainly a possibility we're dealing with a very unstable object. This is the survey that was taken at the Euler conference in 2007. How confident are you that Euler flows can develop finite time singularities? Confidence level from 0 to 10. A lot of zeros, quite a few 10s. Take your pick. This is a pretty balanced chart, actually. I'm not sure what this would look like if we took a sample here. How many think there is a singularity in Euler? In Euler.
We now have to, I would have to have a condition on that now.
Okay. How many have a conditional belief? Okay. How many think there is no singularity in Euler? It's interesting. This chart is skewed now with this side. Well, that's very interesting. Okay.
There's also a singularity in number 7.
Oh, yeah, that's on the fence, Well, numerical evidence. This has been a great stimulation to the field, let's face it. Bob Kerr's work, I just mentioned off the bat, there have been many people, but that stimulated me a lot to think about this. High symmetry flows, Taylor-Green's original paper, Taylor series in time, few terms, a little bit of growth. I really started us thinking about this, Brachet and all, continuing that work. Kita's high symmetry flow pelts going on with that work. Cut off too soon from really getting to the end of it. Axisymmetric flow with swirl keeps popping up as a candidate. I'll come back to that a little bit. Antisymmetric vortex filaments, the sort of picture that we just looked at. Sijian, Premier, Kerr, looking at this kind of these structures and how, and many other people. This is a very partial list. Other geometries like Lamb dipoles. These dipoles, there are various names, Chaplagen, Lamb, and you also see it in Batchelor's book, those little two-dimensional dipoles, but you turn them into three-dimensional objects and you put them at right angles, let them collide. General conclusions, well, maybe this is probably not too accurate, but I'm just saying no clear-cut indication of a finite time singularity. Modest growth, but definite growth, sometimes pretty dramatic, and then some indication of this critical time dependence that would put it into satisfying the borderline of the BKM criterion. I'm going to focus first at least on mutual action and anti-parallel vorticity distributions. And then we'll take a look at axisymmetric flow without swirl. And that's, just pure axisymmetric flow like a vortex ring or something. And then I'll add some swirl, but I really want to move. Well, we're going to consider something of a Taylor-Green sort of problem. And then an associated problem in Boussinesq convection of a stratified flow. And then finally, I want to come back and try to embed some of these arguments into 3 dimensions with a little caricature of what, is a possible way of thinking about a singularity. And I'll tell you some sort of speculative thinking on that anyway. So here are the equations of, first of all, axisymmetric Euler flows with the theta components indicated of vorticity and velocity and the radial and, radial and z is the axis. And the key thing here is that this is the swirl velocity. This term is forcing the creation through the vorticity equation of the theta component of velocity. If the swirl is 0, so we have axisymmetric flow without swirl, then we get this invariant. And this is the other invariant. That's really basically Kelvin's theorem for that swirl. And so these are the equations. And I want to get rid of the swirl now. But first, let me just mention, well, this is no swirl. These are 2 colliding vortex rings. And these are the old 19th century calculations of all these rings. And they considered colliding vortex rings. And if they're separated by distance, well, I didn't even put it there. That's d. D is the separation. R is the radius of the ring. And if you turn these things up, the separation goes down to 0. These things collide before they've really gotten all that big, maybe 2 or 3 times their initial length. And this coming together of these rings is a crucial thing one has to deal with. And of course, we saw in that film how the rings sort of explode. They come together, and then they sort of get mixed up, and something is going on there as they interact. We'll be hearing, by the way, after Hamas will be telling us a lot more about the 3-dimensional questions that arise for interacting vortex filaments and the questions that come up there. Now, we know that we've heard this before, that axisymmetric flow without swirl is globally defined in time, and therefore there's no finite time singularity and so on. And a proof of this is given in the book by Bertozzi, Maida and Bertozzi. And I'd like to just go through this quickly because it's very simple. Oops, I keep hitting the wrong button here. You have the Biot-Savart law, and you can divide it up into 2 pieces separated by a sphere radius r0. And in each one, you can, I was told once that at in the lecture hall for where they deliver the first lecture as a fellow of the Royal Society, there's a step like that, and somebody was giving a lecture, and every time he fell back, he changed subject. So this is sort of the modern equivalent of that. Anyhow, so you can divide this up, and see, all you're going to use is the order of the kernel here. And in the first one, the first part, you just take the maximum of the vorticity over its support out, and you integrate out the rest. Wait a second, yeah, I guess that's okay. You get an R0. And then here you integrate the vorticity and pull out everything because you're so far away from the origin and so on. And then you decide, well, this V0, that's the support, the volume of the support of the vorticity, I can choose that R0 in terms of that, and that's what you do. And then you get out that the maximum, dRdt has to be less than or equal to the maximum of u, which is less than or equal to RT, and you get an exponential bound. Okay, so the bound here goes as e to the t, or e to the constant times t. Well, you can do better than this, and this is the kind of point I'm trying to make. I'm not trying to use this example as anything too important for this problem, but it can tell us the kind of thinking that needs to go into answering the more complicated problems. And in this case, we've not used much of this kernel structure at all. So the mathematicians have to come in and help us with that kind of structure and getting its implications. Now, I did something very simple. I wanted to consider just the fact the following fact that so let's take a target ring. We're going to try to figure out how fast this ring can go, how fast it can expand. That's our target ring. We don't care what we do with the rest of the vorticity. We can use it in any way we want kinematically. There's no dynamics here, okay? Well, how do we get vortices? We have positive and negative rings, okay? Well, we can take the biggest positive ring and the biggest negative ring, and we could fill up, in a way, a space of kind of toroidal, I call it a cocoon. Peter Constantine suggested this term, around the target ring, consisting of this maximized, if you like, vorticity, positive on one side, negative on the other, so it's pushing it with a maximum velocity. And the constraints here, if it's just the volume, okay, and then you have the maximum vorticity in the starting point, you have the invariant that says the vorticity grows like the radius out. So we have all this control just with the volume. And if we do that, the result is that here's this sort of cocoon as it develops. This is sort of, I mean, this is not, the scales here are all distorted, but anyway, it's kind of a circular thing. There's a plus one and a minus one. You see that in the target vortex that it's pushing is right along here. And this thing develops as it moves out. Of course, it's getting smaller because the volume is being conserved, but the vorticity is getting stronger and stronger. It's proportional to the radius. And so you end up with a t-squared bound. And this can be proved. And so it's just using the, oh, this didn't come out very well. This is a sort of cartoon of this. Now, the cross-section here is one of these Chaplin-Lamb two-dimensional vortices, basically, which scoot along with a certain velocity, which depends upon the radius and the vorticity inside. And you can work that out. The vorticity is growing like r. The radius is growing like 1 over the square root of r. So the velocity is growing like the square root of r. And so all the velocities are like square root of r, including the velocity that speeds out. So dr dt is like square root of r. And that gives you a t-squared bound. Now, the velocity being like square root of r and integrated over this small area of area 1 over r gives you an order 1 kinetic energy over the cross-section. That's the kinetic energy per unit length. You multiply it by r, you get r. So the kinetic energy is growing, and this is not then physical, so that bound cannot be really sharp. And so the question is, can you do any more? Well, you can. So I formulated another variational problem that could be solved in an analogous way, a little more complicated, using just conservation of energy. And it ends up there that this is a different shape structure now, so it looks like this. These are qualitative pictures. This is our target vortex right here. This is now like 1 over radius to the 3/4 instead of 1/2. So the volume's not being conserved, but the kinetic energy is being conserved. But then I noticed that by letting vorticity trail off in a thin layer, just as, in other words, let the blob leave behind vorticity in a thin layer, you can do this and get rid of the vorticity and conserve, if you like, the volume without changing the energy estimate. So this is sort of an artificial way to get a maximizer with the t to the 4/3 growth that satisfies both of the constraints. Now, this is a slice through one of the numerical experiments. I forget which one it is. I think it might be from Howe and Lee, and then there's Shelley and his collaborators have something similar. I was talking to Bob Kerr. I think that the slides he showed the other day indicate something similar. This is sort of the cross-section through the plane of symmetry of anti-parallel structures after they've developed a while. And there is sort of, what I'm trying to refer to is that there is sort of a hump here and then something trailing off. And there was also in the movie all that material that's left behind. You see from the expanding vortex, you see a sort of sheet of stuff that's red. That's something that's trailed out as it's expanded. So that maybe this is not too offbeat, but anyway, it's probably not at all sharp. The question is, can someone do better? I'd like to answer this question for axisymmetric flow without swirl. I have a conjecture that I am not sure I mean, it's not something I feel very strongly about, but it's come to my mind several times looking at this problem, and that is that it can grow at most as fast as t, and the reason being that I think it's sort of being compressed down to a thin sheet. Some of these structures, I'm sure people here can straighten me out on this if I'm wrong. And if you do that and you get these sort of dimensions, then you get an estimate that it's going to only move like t. In other words, with constant velocity. Another thing that can, by the way, if you study two-dimensional vortex sheets like this, and you try to do something thin, you find that you sort of get a Berger's equation type behavior, and you get a shock. And what does that shock mean? It means that the stuff is going to roll up into two pieces like this. I mean, it's something that's going to eject out and start a roll up. So another possibility might be that you compress these things as you move out, you roll up, you get a sort of nose that can push you along a little more, but these things compress, then you roll up again. I mean, it's just a thought, okay. Well, what about axisymmetric flow with swirl? I'm going to have to hurry. Yeah, okay. Well, the growth mechanisms of interest. We can advection of omega theta over r radially outward. That increases u theta. We can intensify now. We have the opportunity of intensifying, darn it, by this term here. And we have radial advection of r theta, of u theta rather, toward the axis of symmetry and blowing up as through the conservation of r times u theta. All of these have been thought about by people. What I want to do here, this is actually in an old paper of mine, and I thought about just reviving it because it seems to me sort of relevant to the question. And the question is this: when do you get sort of false signals of a singularity by doing a calculation that is really not going to be there if you wait long enough, okay? And this is an example of that, okay, I want to consider. And what I did was truncate the radial momentum equation by just getting rid of the acceleration terms, okay? So we're just left with the PDR is the centrifugal pressure, basically. And then I thought of an axisymmetric with swirl version of the Taylor-Green problem. Now, the Taylor-Green problem was formulated in a rectangle or a cube, and the initial vorticity is basically a twisting back and forth of a vortex in a square channel, if you like, with a certain period. Now, if you take the zeros and you separate them far enough compared to the size of the channel, and now we'll take that channel and turn it into a cylinder, we have a problem that I like to consider, okay? And so the initial swirl velocity is given only. That's r times the sine of an epsilon times z, where epsilon is a small parameter in the cylinder. And now we'll have a bounded domain, r less than 1. And the idea here is the vortex lines that are in the sort of middle of the where the swirl is maximum have to leave in order to make way for the vortex lines going the other way past these planes 0, pi, 2 pi, and so on. And at the same time, the vortex lines are creating a rather large pressure due to centrifugal forces, and that pressure is positive here. It can't be here because there's no swirl velocity. So it's going to push things along here, carrying with it the intersections of the vortex lines with the wall. And so things tend to pile up on these planes, and that's what was seen in the later calculations of Taylor-Green in the rectangular geometry. And that's what I want to consider here. And if you do that, you get the equations. Oh, I'm sorry. Now I want to go to I want to do something else. A Boussinesq approximation. Let's imagine I take the cylinder and I decide that instead of considering the flow in the entire cylinder, I'm just going to consider an annular region, okay? And then I want to consider that annular region to be thin compared to 1. So it's small compared to 1. And we still have a stretched version of the problem. So we go to a two-dimensional geometry. So we're in an annulus. And when you do that, you can map, and this is, I mentioned the stratified flow problem. This is it. Boussinesq stratified flow, where you have the inertial vorticity is 1, and this is the buoyancy effect and its effect on vorticity. This is the convection of this. Now, what is this representing? Well, the correspondence is that this rho is basically related to the square of the swirl velocity with some factors. And so under this mapping, if you go to infinity, you formally go into this Boussinesq problem from axisymmetric flow with swirl. So there's a formal limit there that makes this a sort of model to be considered. And E and Shu have done calculations of rising bubbles in this stratified flow, which represent a certain, if you like, limiting Euler problem. And they found, rather fast, probably exponential growth of vorticity, but no singularity. Okay, so that was one indication that there's no singularity here. I'm just going to skip through this, but basically there's an Euler-Lagrange variables you can insert to change the equations to something that is a little more tractable. You can do a numerical solution of this. But one thing very nice is that you can get an exact asymptotic form on the surface of the cylinder near the critical planes where things are going infinite. And the solution there looks like this. It is blowing up. And you see it blows up in a way that's consistent with Biel-Kato-Mito, and it looks just like a singularity. And when I submitted this paper, one of the referees wrote back, accept this right away. This is a discovery of an Euler singularity. I had to write back and say, no. This is not. This is the breakdown of two-dimensional flow into three-dimensional flow. This is a false singularity. And of course, then I had trouble getting the paper published. Well, I did. It was finally published, but anyway. Anyway, that's a false singularity. It will surely disappear, but it'll look like, okay. Now, something sort of cute quickly. I've just been playing with this. This is now a solution in a finite domain for this Boussinesq convection problem. So you can think of it as a limiting case of axisymmetric flow with swirl in an elliptical shaped torus, with a torus with an elliptical cross section. What it is you take a linear, a constant stratification of the fluid, okay, and the vorticity, the stream function has this form. The vorticity is constant. It's just a function of time. And the gamma is such that it gives you an elliptical boundary. And so you can start out, say, with theta here equal to pi over 2. So you have all this heavy fluid over here and light fluid here. And the darn thing moves like a pendulum, okay? Now, in the circular case, it is exactly a pendulum. It just sloshes like a pendulum. And theta satisfies the pendulum equation with a certain period, okay? Here it would turn out to be alpha over, the period is alpha over square root of 2 or something like that. Now, this was, by the way, Maida and Scheffer considered this in their work on atmospheric instabilities in the infinite domain they used basically the spherical case. And I mentioned this to Maida. He'd never seen this. It's a trivial thing, but it's sort of cute because it means as the flow develops, you can change. In other words, as these lines of constant density stay linear, so they squeeze together as you get to the thin part of the ellipse. They open up as you get to the thick part of the ellipse. And simultaneously, the vorticity is changing. And both of these quantities can get arbitrarily extreme in the limit of arbitrarily thin ellipse. So you can get a periodic solution of these equations that goes to arbitrarily large vorticity periodically. Anyway, the question really here is what to do with something like this. It's a nice base flow, and I think there are perturbations, particularly as you try to embed this in axisymmetric flow with swirl that could be interesting. There could be some modes that might give rise to some interesting growth patterns for vorticity. And like I say, the whole point is to try to get your handle on something that you can study for a long time. That's just the oscillation. Now, quickly, I want to talk about, try to think of some of these ideas and put them into 3 dimensions. And you can consider the motion of a line in the plane. Now, I want you to think of this line not as really a line. There's going to be a lot of structure when we cut through this line and look with a microscope, okay? But there's a lot of structure there that's going to be quasi-2-dimensional that's going to do something to make that line move. And all I'm assuming is that kinematics of a line in the plane, and I'm going to add here the stipulation that the Jacobian, the rate of stretching, which is the partial of S with respect to S0, coming back to that notation, is proportional to a power of the normal velocity. Okay. Now, for that case of volume constraint that we had before for the axisymmetric case without swirl, that beta would be 2 to do that problem in this geometry. For the case of conserving energy and volume, that would be 4. That would correspond to t to the 4/3 in the axisymmetric case. But I just want to have this law. I don't want to restrict it to be axisymmetric. We kind of look at the evolution of a line. Again, this is work from a paper in that Euler meeting, but I've never really talked about it, so I thought I would do it here. Here's the equation for the normal velocity you get when you put that information together. And the interesting thing is that you have a beautiful similarity solution. You wouldn't think this would be boiled down so far. But it's a similarity solution. There's a gamma here in the velocity. Gamma equal to 2 corresponds to Biel-Maida critical. That corresponds to J going as, J goes as tau to the -2 gamma, which would then be 1. And that would correspond to critical Biel-Maida. Now, the restriction that this works is that gamma be greater than or equal to 1/2. If it's greater than 1/2, you've strictly satisfied Biel-Maida. That's a good one. The BKM condition. And let me tell you that the thing here boils down to this equation right here in terms of this G. And so then you can look at what the line is actually doing. You have control of the velocity here. And so let me say one more thing before going to the next slide. If gamma is greater than 1/2, however small, above 1/2, the line is growing. In other words, I'm thinking of this as a structure, 2-dimensional. So as it stretches, it thins down, conserving volume, okay? That we know, that we have to do that. And for gamma greater than 1/2, what's going to happen, even though this thing is going to a singularity in finite time, is that it always stays quasi-2-dimensional, if you can imagine that, okay? And so here's what happens. It's an infinite structure going off at a certain asymptotic angle. And as time flows, the line moves to comes in, always asymptoting at the same point. And finally, at the critical time, reaches a point where vorticity is infinite, staying locally 2-dimensional. It goes infinite at that point. And another thing is that the total stretching, if you look at the total stretching that's occurred, it's finite. Okay? Now, you can criticize this in a lot of ways, and I'm not claiming that we should. Yeah, Charlie. You have 5 minutes? Oh, 5 minutes. Okay, that's all I need. I'm not saying that this is, but let's keep in mind, Euler singularities can be very, very hard to find. Any structure we talk about could be very, very, very unstable. And I know this would be very unstable, regardless of what the structure is locally, okay? The other criticism would be, and let me start going to this here. Well, I'm just saying a few things, which maintains the motion law. Well, I'm not sure that a power law is right. Maybe there's some other law. But anyway, core deformation may destroy self-similarity of the cross-section, blah, blah, blah. I mean, it could easily happen that this could be destroyed. And then there's axial flow due to pressure gradients occurring. I've looked at all these things a little bit. What I want to say now, let's see. Is there another one? Oh, okay. This is really my last slide, but I wanted to comment on these things. What I have attempted to do, and there is a paper. It's on it's sitting somewhere on my website, but it's been languishing there as I try to figure out what to do next. Is to introduce a local geometry along this line and solve. You see, we have local two-dimensionality possible here, so we're going to perturb around local two-dimensionality, and there are ways of doing this using contour averaging techniques. There's this Schwartz symmetrization idea and so on. And you can do that, and you get a horrendous set of equations. These are called variously generalized differential equations, queer differential equations, pseudo-differential equations. You see, we're talking about some closed contours. They have to be followed, and only by following the contours can you compute the solution, although the contours keep deforming and the quantities are sort of tied via conservation laws to these contours, and so you have to keep track of all this, and it gets out of hand, quite honestly. But I was trying to move into what I envisioned as a singularity. Okay, keep that in mind. The other thing is we saw that simple volume conservation does not conserve energy. On the other hand, there is only a finite amount of stretching in this object. Only a finite amount of energy has to be supplied. It's conceivable it could come in from this structure, via flows along the structure. So there are all these issues. Now, I did look at axial flow using some models, and I believe that is not a big constraint on understanding this problem. There's some approximate procedures that indicate that's not going to be troublesome. What is really troublesome is core deformation, and that it may be what kills everything. But anyway, that remains to be seen. Another line of investigation is to think that, well, since this is probably so darn unstable, why don't we start at the singularity point and move back in time, see what can be done mathematically there. That's something else to think about, because we could start with a known structure like the Chaplygin-Lamb vortex. It's going to, in negative time, is going to do something horrible, and maybe too horrible to do anything with, or it may not. I just don't know. I'll stop there.
Time for questions and comments. I'll ask the first one. What's your opinion of, what's your guess about singularities?
I think I would say...
You notice how he didn't offer his own opinion?
You're the perfect straight man, Charlie. I sort of believe in a singularity in the weak sense, if you like.
No idea what you're talking about.
Not a weak solution, but in the weak sense. That is to say that it's an elusive object if it does exist, and it will probably be buried in a lot of stuff that is non-singular, and I see it as a huge saddle point. And how do you get there?
Okay, I'll ask another question, a little more technical. So you've been focusing on these systems with a lot of structure and symmetry, sort of reduced dimension dynamics here. Well, what about, what do you think about vortex lines crossing, reconnection problems, things like that? Is there something there? I mean, there you're going to get things twisting themselves up, presumably, into...
You mean, would that be a source of...
in
in other words, this is sort of saying maybe the Navier-Stokes problem is the right problem.
Or, not even
the singularity.
Well, not even Navier-Stokes. Do it in Euler. Set up the reconnection problem in Euler. Finite core vortices.
And do reconnection.
And do reconnection.
I haven't thought about that, but I mean, that could lead to something definite. I mean,
That would be nasty.
It could be that. I mean, particularly if you have knots and so on.
What is, oops.
Well, I hear, oh, there.
Yes, what is your impression about the role of the wall? I'm talking about wall even in Euler, because in Euler, wall you cannot penetrate.
Yeah.
But you're not a structure.
Right,
In Navier-Stokes, of course, no.
That's a very good question, Mary, and I really would like to see this answer myself. I don't know how you feel, but I'd like to see this answer without any walls in Euler. And you saw in that problem with the pendulum, that change of vorticity is being driven entirely by the walls. Okay, so I mean, that's an example.
My personal belief is that you need wall, and then you will.
Oh, but you need walls in the singularity.
And yeah, exactly. That's the
Oh,
point.
that's it.
The chance for singularities because of the wall.
I see.
This is my bet.
In
Even
other words,
for Euler, because the non-penetrability gives a kind of.
so there's something about the reflected flow that is going to be important in this idea.
But then could you not set that up without a wall with some psychotic
Well,
image?
my kind of feeling is more like if you have a wall, even in the fact that it cannot penetrate. If you take like a Kelvin-Helmholtz instability on it, the non-penetrability obliges the Kelvin-Helmholtz to kind of detach. I mean, this kind of singularity detachment from the wall. It's something really important, even in some.
Where's Sahan? Yeah, why don't you come up and start doing this? Any other questions or comments for Steve? Yes, right here.
Understand your work on vorticities that you don't believe that singularity and potential flows. This is impossible.
Yeah, I do. Yeah, right. It's interesting that Ed Spiegel and I, back in the 70s, produced one of these infinite energy Euler flows that blows up in finite time. And we started looking at this like crazy and hoping that we could somehow embed it in something that was both vorticity and, there are all these other infinite energy solutions which are not potential, which also give finite time singularity, Stewart's work and so on. But they are not physical in the sense of having infinite energy. That's a no-no.
Great. Thanks, Steve.